Hello everyone, welcome to Unit 3, Day 22. We're going to do some more mixed review today, again focusing on sampling distributions and confidence intervals. So yesterday we did a sampling distribution with the mean, so we're going to do one with the proportions today. Also yesterday when we reviewed confidence intervals, we did a confidence interval for proportions, so we're going to switch over to doing confidence intervals for means today, so we'll see an example of that. All right, so let's go ahead and jump right into the problem for today. So it says, according to the New York State Board of Law Examiners, approximately 61% of people taking the New York bar exam pass the exam. All right, so 61%, whenever you see something like this, like a 61%, like they'll say like 30% of people smoke or, something like that, they're giving you a proportion. All right, this is a proportion, even if they don't expressly state it. So this is a proportion of people that did something. All right. So that means we're probably going to be finding a probability that's related to a proportion. All right, and that means we'll probably be using a sampling distribution for the proportion. So let's see what we got here. It says if 12 people who have taken the New York bar exam are randomly selected, what is the probability that 79% have passed? All right, so this is going to be an example where we do the sampling distribution because we are taking multiple people. So in yesterday's video, we kind of talked, how do we know when to use the sampling distribution? And I said, well, if we're taking multiple things at a time and calculating a statistic based on that sample, and we keep on doing that over and over again, right? So in this case, we're taking 12 people, we're looking at how many of them pass or what proportion of them pass, and we would take another 12 people, do the same thing, another 12 people, do the same thing. And as we keep collecting these proportions, right, and placing them on a histogram somewhere, they will create a distribution. As it turns out, it'll create a normal distribution. And typically it will normalize perfectly once this number gets above 30. So this is a pretty small sample size. This probability might not be as reliable as we like it to be, but we can still do it. All right. So the center of our sampling distribution, right? So we know the shape is going to be normal, but the center of our sampling distribution is going to be whatever we get here, right? So whatever they say the population proportion is, right? So that's going to be 0.61. That is the center, and they want to know what's the probability that at least 79% pass, right? So 0.79 would be over here, right, to the right of the 0.61. And then we want at least 79%. So that means that we want everything in this right-hand tail, right? So we're doing a normal CDF. Right, and the things that they're going to want to know for the normal CDF, they're going to want to know the left bound, right? So that's going to be 0.79. Right, so we'll say left is 0.79. The right bound, since this is at least, it can be anything bigger than 0.79. So we're going to go from 0.79 essentially to positive infinity. So in the calculator, when we enter that in, we're just going to say 1e99. That lets the calculator know that we're doing infinity, since it's a ridiculously large number. And then it's going to want to know, okay, well, what's your center? What's the mean that you're using? So we're going to say that's 0.61. So we'll say center is 0.61. And then the last thing it's going to want to know is what is your standard deviation. And this is really the only tricky part that we have to deal with. So when we are working with a sampling distribution for the proportion, to calculate the standard deviation, we have to do the square root of PQ over N. All right. P would be essentially the number or the proportion of success. Okay, so that's going to be 0.61. Right, and that comes from the population, so it's going to be 0.61 times the probability of failure, so that's going to be 0.39 over our sample size, which is 12. And this will all be inside of the square root. Okay. All right, so again, just to clarify that 0.39, you find that 0.39 by taking 1 minus whatever p is. So we would do 1 minus 0.61, and that would get us that 0.39. All right, so we would multiply those. Let me grab my calculator here and let's do that calculation. So we're doing 0.61 times 0.39. I'll just go ahead and hit enter and then divide by 12. And then we'll take the square root of that. And so we get 0.1408. There we go. So we should have all the information we need for our normal CDF. So we're looking at the probability that X is greater than 0.79. And so I'll go to my calculator. Let's do that real quick. So we're going to do a normal CDF. So we're going to go second vars. And then normal CDF is option 2. It wants to know the lower. So we said the lower was 0.79. The upper is going to be 1E99. So to get the E, it's right here. It's the comma button, but you have to hit second first. So 1E99. And then for the mean, that's going to be 0.66. And then our standard deviation will be 0.1408. And then we just paste. There we go. So we got 0.1779. They want 4 decimal places. So yeah, 0.1779. And there's our probability. All right, so let's take a look at the second question here. Again, using the same assumption about the population proportion being 61% here, now we're looking at if I were to randomly sample 44 people, if I went and looked at 44 randomly selected tests, what's the probability that 79% of those people would have passed? So everything is the same here. The only difference is the sample size has increased. Okay, so the sampling size increasing, we are dealing with a different sampling distribution because remember when we drew this one, we were taking 12 people at a time, right? And finding the proportion, plotting it, finding 12 more, finding the proportion, plotting it over and over again. And that's where this distribution came from. So now we are dealing with a different distribution. And the only difference when we create this distribution is we're taking 44 people at a time. And what that means for the shape of our distribution is that we're going to have a skinnier normal curve, right? So we're going to have something that is more compacted around the middle. I can't draw with this stupid pen. So let's see. So something like that. That works. All right, so a skinnier normal distribution. It's going to have the same center, right? So here's our center at 0.61. And again, we're still trying to figure out 0.79, right? At least 0.79. So we're trying to get this area to the right of there. Okay. So again, normal distribution, more concentrated around the middle because the sample size has increased, but everything is going to stay the same except for the standard deviation, right? So when we go to set up our normal CDF for this one, it's going to be normal CDF. The left is still going to be 0.79. The right is still going to be positive infinity. The center, or the mean, is still going to be 0.61, but we do need to recalculate the standard deviation, right? This is the thing that tells us about the spread. It's essentially trying to tell us, hey, you got a skinnier curve, right? So we're going to set that up. We've got PQ, so this is going to be 0.61 times 0.39, just like last time, because our assumption about the population hasn't changed, right? We're still expecting 61% to pass, which means we would be expecting 39% to fail. The only thing that changes in this calculation is what we divide by, and that's going to be 44. Okay. All right, let's see what we get for a standard deviation. So we're going to do 0.61 times 0.39, enter, divided by 44. There it is, and then we square root. Ironically, when we square root here, we get a bigger number. All right, so we get 0.0735. 0.0735. There we go. So there's our standard deviation, and now I have everything I need to go to do my normal CDF. All right, so I'm gonna pull up my calculator here. Let's go second vars. We'll go to normal CDF. All right, and everything's gonna stay the same. The only thing that changed was the standard deviation. That was because of the sample size. All right, so we're gonna put in that 0.0735. Hit enter. And enter one more time. There's our probability. So we're going to say the probability here that x was greater than 0.79 was 0.0385. There you go. And you'll notice going from one to the other here, we had a 17% probability when the sample size was, relatively small with only 12 people in the samples. And then the probability got much smaller as we increased the sample size. Okay, so when that sample size increased to 44, the probability went down considerably. All right, you have to remember we were expecting, you would expect 61% to pass, right? So no matter what sample size you grab, you expect 61% of that sample to pass. So trying to see how many would be at 79%, right? You wouldn't expect too many samples to have 79% of the people passing, not when you expect the pass rate to be 61%. All right, so the reason that probability got smaller, again, was because we increased the sample size, which concentrated the data more around the middle. So moving more of the data from the tail towards the middle means this area in the tail is much smaller than it was in the previous problem. All right, so there's some conceptual things to understand there about what's happening to the shape of our distribution, and that kind of explains why the probability changed the way it did simply by increasing the sample size. All right, so there's a lot of connections happening there. All right, let's move on and talk about confidence intervals. All right, so again, when we do confidence intervals, we are estimating something. All right, so we're estimating something. Usually it's a proportion or a mean. All right, those are the only two things we have taught you to estimate. All right, so it's going to be one of these two things, and you have to read the problem and think, which one am I estimating? All right, so let's read. So it says the table below contains the birth weights in grams of 26 African-American babies born at Bay State Medical Center in Springfield, Massachusetts in 1986. All right, so they want us to compute a 95% confidence interval for birth weight. All right, so we're going to be doing a mean. All right, we're doing a mean, and the question is, we either know the population standard deviation or we don't know the standard deviation. Okay, and I'm looking through the problem here. They give me some data, right? This is a sample with some data there, but they do not tell me, right? They do not tell me the standard deviation for the population. So this we don't know this. All right, and what that means is we're going to be doing what's called a t-interval. All right, if we did know this, we would use a z-interval. Okay, so we're going with this one. We're going with a t-interval. We don't know the population standard deviation. We're trying to estimate a mean, so that's the one that we want to go with. All right, and you'll notice that there are some questions, like it says find the point estimate, right? It says find the margin of error. So we're going to go to our calculator, and we're going to calculate our confidence interval first. And I'm going to show you how to get those things from your confidence interval. All right, so here we go. Grab our calculator here. Calculator is very important. All right, you should know how to use this. You can do these problems in about 1 or 2 minutes if you know how to use this thing. All right, so you notice here they gave us raw data. They didn't tell us what the sample mean was. They didn't even tell us what the sample standard deviation is. We've got to go and find that stuff. So we're going to go over here to stat, and we're going to go over to tests. And I just want to show you where things are at, right? We're looking for t-interval, right? And that is option 8, okay? So the question is, did they give us data or did they give us the stats? Well, they gave us data, all right? So we have the raw data over here, all right? So we're going to be using the data option, which means we need to put our data into L1 or whatever list you want to use. So before we go any further with the t-interval, I'm going to hit Stat, and I'm going to go to Edit. Okay, and in L1, you're going to enter in all of your data here. All right, so this might be a good time for you to pause the video and go ahead and enter in your data. Okay, hopefully you did it. So I've got mine entered in here, so I'm going to go back to my test menu. So you hit Stat, go over twice, and then we're going to go down to t-interval, hit Enter, and I'm going to tell it data. I'm going to tell it that my data is in list 1, and then it wants to know what confidence level you want. No problem. We want 0.95. And in case you missed that when we read the problem, right, they wanted a 95% confidence interval, so that's where I got that from. And we're going to go down to calculate. It's got to work for a little bit, so there we go. So now we have a confidence interval, and it gives us some information here, and we'll come back to that in just a minute. But first, let's get this confidence interval jotted down. Okay. So they want the confidence interval down here. Notice they tell you what form they want, so they just want that interval form, which is exactly how the calculator gives it to us. So we're going to say, we're estimating that baby weight to be in between whatever two numbers I put here. All right, so we're going 2955, and notice what they want us to round to, the nearest integer. Okay, so if this is 2955.7, then we're going to say the nearest integer is 2956. And then the other end of our confidence interval is at 3378.3, so that's not quite big enough to round up, so we're just going to say 3378. Okay, so this is our confidence interval. All right. Now, to go back and get these two things, the point estimate, I like to think of this as the midpoint. This is the midpoint of our confidence interval. It's what's directly in between these two numbers. It's also the mean of your raw data. Okay, so it's a midpoint or the mean of the data. And they give us that number right here on the screen. So this is our point estimate right here, 3167, right? So we would say X bar, right, because it's a sample mean, and that is 3167, and that's also the midpoint between these two numbers. Okay, now the margin of error, right? The way to think about this one, once you calculate your confidence interval, it is the distance from the point estimate to either one of these numbers, right? So you can say to one of the bounds. Okay. And I know Mr. Van Slyver showed you another way to calculate this, to calculate the margin of error manually. So like there will be times like if you didn't have a calculator and you had to calculate things by hand, you would go point estimate, then calculate your margin of error, then use the margin of error to calculate your confidence interval. So we're kind of going backwards. We have the technology, so we're constructing our confidence interval and then working our way backwards to get a margin of error and a point estimate. All right, so this is a little bit different than what Mr. Van Slyver has shown you. I'm just making sure you see all the different ways that you can go about doing this so you can pick the easiest way for you. All right, so the distance from the point estimate to one of the bounds. All right, so if I take one of these numbers, and I'm going to grab the decimal number, so 3378.3, and I'm just going to subtract the point estimate 3167, right? And that would get me that distance, right? It's the distance between the point estimate and one of the bounds. So let me grab my calculator and let's calculate that. So we got 3378.3 minus 3167. There we go. So our margin of error is 211.3. We just say margin of error, so we just say ME equals 211.3. Okay, so another way to state our confidence interval is we can say the estimated birth weights for African American babies at Bay State Medical Center is 3,161 grams. plus or minus 211.3 grams. All right, so that is our margin of error. This is our confidence interval. So we've calculated all the numbers every which way, right? So now what we want to do is we want to do a little bit of interpreting. What does this number mean? What is it telling us? All right. So it says babies weighing less than 2,500 grams are considered to be of low birth weight. Can you conclude that the average birth weight is greater than 2,500 grams? And so if I'm looking at the confidence interval, right, we are estimating, the birth weight, the actual birth weight, to be in between 2956 and 3378. That interval itself is way above the 2500, right? The 2500 is way to the left of 2956. And so I would say yes, because it says, is it greater? I would say yes. And the reason being is because the entire interval is greater than 2,500 grams. Okay, if I had constructed an interval and 2,500 grams was within that interval that I made, then I would not be able to conclude that it's greater than, right? I would say, well, it could be that number because it's in between the confidence interval that I made. Okay, so it's in between those two numbers, but in this case, it's not. It's way less than the interval that we made. So we can say that it's definitely greater than. All right, so then if we were interpreting our confidence interval here, just to interpret this thing, we would say we estimate so we estimate the mean weight of African American babies born at Bay State to be between 2,956 and 3,378 grams with 95% confidence. Or you could say we estimate with 95% confidence. So you could take this piece and you could put it here if you wanted to. It really doesn't matter where it goes. But feel free to use my statement here kind of as a template for your own interpretations in the future. But you want to make sure that the main points that you want to make sure you hit are, what is it that you're estimating, right? So I noticed I said specifically the mean weight, right? And then to add context, right? So the mean weight of what? And make sure you state your confidence interval somewhere in there as well as your confidence level. Do not say anything about probability. That would be wrong. All right. So, all right, guys, if you have any questions, let me know in the Zoom chat. That's it for today's lesson. Have a great day.